What makes a bad graph bad? Graphs and statistics are powerful tools that allow us to see the data in a visually appealing and understandable way. Often, a graph makes it easier to identify trends or patterns that may not be apparent just by looking at the data itself. Sometimes, though, a weakly designed graph can undermine its purpose. Many times when starting a discussion about bad graphs, it's common to show examples of really bad ones, often combining different kinds of, badness. I'm going to take the approach of looking at it from two angles: aesthetics and integrity. Aesthetics refer to the visual appearance and design of a graph. Some graphs just have bad taste. Some of the things that may contribute to poor aesthetics are cluttered visuals, inconsistent colors, inappropriate use of text or fonts, poor readability, too much going on, and sometimes, they're just weird. Integrity is a much broader category that focuses on the fundamental aspects of making sure that the data is represented correctly. Let's look at a few examples. Here is a graph from the Alabama Department of Labor that displays historical unemployment claims by week. The data is given as a table with two variables. One contains dates, and the other contains the number of unemployment claims. The primary problem with this chart is that it is almost impossible to determine trends in the data over time. This is an example of where data are presented with the wrong type of graph. Something like a line graph would be more appropriate. There is such a thing as too much data, or at least trying to stuff too much data into a chart. The Unicode Consortium released this pie chart showing the most frequently used emojis. Perhaps you can infer some information about 2 or 3 emojis from this chart, but most of the information contained in the chart is unusable. A good rule of thumb is that if your pie chart contains more than 10 segments, then another type of chart is probably more appropriate. The problem of cramming too much information into a single graph is not restricted to pie charts. Let's say that someone wanted to compare the quality of drinking water of, say, Laos and Brazil. How long do you think it would take to infer that information from this graph? Statistician Nathan Yao stated that if you see a chart drawn in 3D for no reason, then you probably should question the data, and perhaps even the chart maker. Although 3D charts may look elaborate, it is often difficult to get real information from them. When you look at this chart, can you determine how high the various blocks are and what frequency each is supposed to be? In his excellent book, Envisioning Information, Edward Tufte described a principle around what he calls chart junk. This principle essentially states that every chart should be stripped down to the minimum. Just show the data and nothing else. One chart junk example in his book is a graphic from Time magazine depicting the average price of diamonds. Tufte proposed a corrected, stripped-down version where only the data are shown. The stripped-down version may not be as flashy, but certainly it is easier to infer information from it. Let's note one thing about the revised version. The scale on the y-axis doesn't start at 0. This isn't always bad, but it can often lead to a pitfall known as the baseline fallacy. A baseline fallacy occurs when information in a graph is intentionally misleading by exaggerating the difference between data values by using a baseline other than 0. For example, the following graph, prepared by a certain U.S. political party, published this bar graph which appears to indicate a sharp increase in the number of Americans receiving federal aid. Notice, however, that the baseline here is 94 million. The same data presented with a baseline of 0 appears to show that the changes are much less extreme. Another way that graphs are sometimes misleading is through the misuse of the area principle. Sometimes images are used to compare amounts. The area principle states that the areas of the images must be proportional to the amounts. For example, if one amount is twice as much as another, its image should have twice as much area. Consider this graph which compares average male height per country. Notice that not only does the baseline not start at 0, but the areas are not proportional to their average heights. This can easily be seen by looking at the figure from the Netherlands and comparing it to the figure from Indonesia. There's only about a 6-inch difference in average height, but when we compare the areas, it appears that it would take about 9 or so Indonesian males to equal the area of one male from the Netherlands. There are many more examples of graphs that are misleading for one reason or another, not the least of which is that sometimes the data itself is questionable. One curious example of this comes from the online dating site OkCupid. We know from extensive surveys that the average height of biologically born males in the US is around 5 foot 9 inches. However, when one looks at the average male height of OkCupid users, who, by the way, self-report their data, the average male height is 6 feet. Now, it may be that only taller men use the online dating site, but it's also possible that there is an entirely different explanation. Can you guess what it is? The bottom line that I hope to convey in this lesson is that care should be taken to try to make sure that graphs represent the data clearly and accurately, without bias, ambiguity, or misinformation. Best of luck as you move on to the next lesson.